I'm calling this a Sunday supplement because it's going to be a supplement to a couple of other videos as well as a transition to some new things that I would like to try. But previously I showed some videos about a signature analyzer, the SIG 101, that seemed to be fairly popular, but one of the problems was apparently the manufacturer and the supplier ran out of them, and for whatever reason it looks like they aren't available anymore. But that's not where I'm going to start. I'm going to start with a follow-on to an earlier video, the last one I did, called Vintage Electrolytics. And on the bench here is a vintage electrolytic, the one at the top, and a couple of modern ones. The one at the top is a 150 working volt electrolytic, an 80 microfarad and a 40 in one can. And what I said in the earlier video was that it may be that too many of us have been replacing these vintage electrolytics when they really didn't need to be, and that the failure mechanisms were actually quite different in the old electrolytics than they are in modern electrolytics. It's not that the mechanisms themselves are that different, it's the statistics that have changed. And what causes that to be true, and I'm trying to answer a few questions that came up. I showed the video to some amateur radio friends or a club, and they had a lot of questions. Some of them kind of got it right away, and some of them I think went away not quite convinced. But the issue that I'm focusing on is the old electrolytics, like this one, were, by today's standards, massive. They had big, thick aluminum cases, and they had wide gaps in the electrolyte, or in the plates actually filled with electrolyte, and so on. And for those reasons, the failure that tended to happen in these electrolytic capacitors, the old vintage ones, and by vintage I'm talking about, say, made 1960 or before, tended to be a slow loss of electrolyte. They would dry out, in other words, accompanied by an increase in equivalent series resistance and a decrease in capacitance until when the unit finally had dried out completely, it was basically an open circuit. It was no longer a capacitor. Modern capacitors tend to sometimes fail shorted. Now, it's not that the old ones wouldn't short. If you applied too much voltage to them, a big spike of high voltage or something, or an occasional manufacturing defect, they would sometimes short, but not very often. As I pointed out in that earlier video, you may want to consider, instead of using instead of replacing all the electrolytics, you may want to just put a fuse in the circuit. These, of course, are modern electrolytics. Notice the difference in size. I'll move this over so that you can get a direct comparison. And you can see this is a 100 microfarad, 160 volt, and this is a 47 microfarad, 160 volt. So basically, these two replace everything this one does, and in about a third or a fourth the size. And so one of the issues with vintage electrolytics is, quite frankly, they were over-engineered. And one of the reasons that the old equipment with all of this stuff was often called a boat anchor, because it had so much metal in it that it would hold the Titanic in a typhoon. But let me give you another example to sort of reinforce the point, and then I'll talk a little bit about what I'm referring to here. Here is another one, an older type. This is a 200 microfarad, 150 volt DC, and I will put alongside it a modern Nichicon, pardon all the motion, these things tend to roll all over the place when you're trying to get them to lay still. And this was probably not even rated to 85C. The Nichicon is rated to 105C, and it's a 220 microfarad, slightly bigger capacity, and 160 volts, slightly higher voltage rating. And yet look at the difference in size. Now, they achieved that size difference by, of course, making things like the electrolytic spacing much smaller. And in doing that, because as I'm sure you know, a capacitor is measured, the capacity is determined by the plate area and the spacing. The voltage rating is based on what causes the spacing to break down. So if there's an electrolyte in between two plates, and you apply too high a voltage, the electrolyte, or the insulation, sometimes called the dielectric, will punch through, and it may cause a short. So let's take a look at that on a kind of a drawing, and I'll illustrate exactly what I'm talking about. Suppose that you have two capacitors. One has a much larger plate area and a much bigger gap between, and the other one has a smaller plate area but are closer together. These two might have the same capacity, but this one will have a higher voltage rating, and this one will of course be a lot smaller physically. Now, if you use the same electrolytic process in this one as in this one, what you might think is, well, as our process gets better, I can squeeze the plates closer together. If I do that, then I don't need to make these plates as big. I can cut the plates off here and here, like that, and I make a smaller capacitor, and eventually I get to this size. But in doing so, you see the danger. The danger is now, if a tiny whisker grows across through the electrolyte, you're going to get a short. Whereas if the same tiny whisker had grown on this one, you would not have a short. That is why that older capacitors, vintage electrolytics, tended not to fail shorted. They tended to fail open, because what would happen is the electrolyte in here would eventually start out with a lot of electrolyte, and then over the years it would dry out. Well, as it dried out, the capacity would go down, the equivalent series resistance would go up, and the capacitor would fail open. Modern capacitors, and once again, I'm not talking about the failure mechanism where they get a voltage spike. A voltage spike can sometimes punch through even the old capacitors. If you had a 150 volt capacitor and you applied a 1,000 volt spike, well, you could get a short in it. But that's not how most capacitors failed in old radios and TVs. Now, NASA studied this back in the 60s. And I had, at that time, access to a lot of these reports, and I found them very interesting, but I think I was the only person that, at the place I worked, who ever even read these documents. At least, let's put it this way, the librarian was surprised when I checked them out to read them, because I don't think anybody else ever asked for them. But the reason that I was interested in these is I had started out doing radio repair back in the 50s, as a high school student. And one of the things that NASA discovered was that as they tried to miniaturize the capacitors, that the failure mechanisms actually changed. And capacitors that used to fail open were now failing short. And the reason they discovered was simply this, that miniaturizing the capacitor changed the statistics in such a way that more and more of the capacitors failed short. Now, why does that matter for somebody doing say a radio restoration? Well, if you're replacing one of these capacitors with one of these, you're actually increasing the chances that when this capacitor fails, it will fail shorted. If you had left this capacitor in and it was still operating, it might still go bad. But if it did, it wouldn't likely fail shorted. And that's what I was talking about in the vintage electrolytics video. And I realize that it is an issue that people are going to debate. They're certainly not going to listen to me. If they didn't listen to NASA, they're probably not going to take the word of a dinosaur engineer. But the reality is that vintage electrolytics are quite different from modern electrolytics. The modern electrolytics are better. They tend to last longer, they tend to tolerate heat better, and they're much smaller. But replacing these electrolytics because you were worried they might fail shorted may be false economy. As I pointed out in my vintage electrolytics video, you might be better to put a fuse in the AC line, which I would recommend you do anyway. Leave the old electrolytic in there, even if you think it might fail soon. Furthermore, a lot of people dislike the idea of jumpering an electrolytic across an old one. That used to be common practice, particularly in radios, and I suspect in television repair as well. If this thing failed open, you just shunt a new section across here. Well, I agree that's probably not good practice, but the reality is that the new capacitor probably would fix the problem, and might fix the problem permanently, because as this one would continue to dry out, it would go more open. And only later, when this capacitor failed, did you have to worry about it, which you would have to worry about whether you opened these up or not. So I have stopped replacing electrolytics in my restorations if they test good, even though I realize that I'm leaving an issue in the radio. But it's not a time bomb in the sense that it's likely to fail. If I put a fuse in the AC line to protect the other components, like the transformers and so on, but I leave the capacitor in and eventually it fails open, okay, I get some hum and I have to go back in 5 years, 10 years later and put a capacitor in. But at least I haven't cut the unit up and so on. Unfortunately, restuffing these old units is a real exercise. So enough on that. Let's change topics. I want to change to what all of this is about over here. You may notice that up there in the upper left-hand corner is an analog discovery and the Digilant breadboard, the capacitor box. So what's all that about? Well, as you'll see in the next segment, what this is an attempt to do is to make up for the fact that that signature analyzer, the SIG 101, is no longer available. What I'm trying to do is to make the analog discovery into a signature analyzer or signature tracer. So let's take a look at that. This is a circuit that I have put together on a breadboard that I'll show you in a second. This is made up of an analog discovery and a single resistor. Now, this is similar to the curve tracer that I made with the analog discovery from a year or so ago that I know some of you built. And in fact, there was even an individual in Europe who built a little board to kind of incorporate this circuit a little bit later, and I bought one from him and did a little review on it and so on. So this is the waveform generator of the analog discovery, and this is channel 1 of the scope, and this is channel 2 of the scope. This, of course, is labeled 2 plus on the analog discovery and 2 minus, and you may want to pause the video at this point and copy this schematic or make some notes or whatever. Then the 1 plus and 1 minus are connected as shown. In other words, the 1 minus is connected to the end of a resistor. I'm currently using a 1K resistor here, and the waveform generator, this is ground. Perhaps I should have written that in there, and I will do that. Okay. Added some notation. This is ground of the waveform generator, and this is W1, in other words, waveform 1 output. And then this is 2 plus and 2 minus, so 2 minus is wired to 1 minus, 1 plus is wired to one end of the resistor and to the ground of the waveform generator, and then the other end of that resistor is connected to the junction of these two pins. So what does this do for us? Well, what it does is it makes a signature analyzer out of the waveform, or out of the analog discovery 2. Now, could you do this with other equipment? Yes, you can. A function generator used here, a 2-channel oscilloscope that can operate in XY mode will work here, but there's one caution. This point has to float. Now you may notice that this was ground of the waveform generator. But if this point isn't floating relative to this ground, then this resistor is shorted out and you will not be able to measure the current flowing through it. The way this works is the waveform generator puts a voltage here. That voltage flows through the circuit and comes back on the red lead and flows through this resistor and back to the waveform generator. Channel 1 of the oscilloscope senses the voltage across that resistor, but that is an analog for the current. In other words, the voltage across this resistor is proportional to the current by Ohm's law. And channel 2 of the oscilloscope is looking at the difference between this point and this point. In other words, it's right across the black and red leads. So let's take a look on the analog discovery or waveforms software, what this looks like. Okay, here is the waveforms software. On the left over here you will see the oscilloscope display, and you see that we have an out of phase sine wave. That is, the blue is one channel, I think it's channel 2, and the yellow is channel 1. So remember, channel 1 is measuring the current, channel 2 is measuring the voltage. To the left, you see I have added an XY display. Now, the way you do that is you just go to the view point up here. Let me show you. If you click on view, you see right here it says add XY. And that adds this window. Now I've adjusted the voltages. I have the waveform generator set to a 5 volt sine wave at a kilohertz, and I have the oscilloscopes set to, I think it's 1 volt per division. Yes. And over here what you see is a resistor displayed. Now I have a resistance box connected to it, and just as with the SIG 101, if you change the resistance, let's go from 1K to a 3K, well, you see what happens. The current, that is the yellow trace, goes down. The voltage actually goes up because the analog discovery isn't loaded as much, and the slope of the line of the XY plot increases. So let's go back to a K, and now let's go to 400 ohms. And you see now the current has increased, the voltage has decreased, and the slope has flattened out. Okay, now let's go back to a K, and now I'm going to put a capacitor across this. Now this is a capacitor across the resistor, that is the load of this device. It's not the resistor that's in series, the one that you saw on the previous schematic. This is across the red and black leads of the signature analyzer. Well, you noticed two things. One, the current and voltage changes, but it doesn't just change in magnitude, it also changes in phase. You notice now that the peak of the voltage and the peak of the current are not 180 degrees out of phase. Well, that's because we've added the capacitor, and that's why that we have this ellipse on the XY plot. Now, let me change that's a 0.1 microfarad. So in other words, it's a 1K resistor and a 0.1 mic capacitor. Now we'll change it to a 0.5 mic capacitor. And you see what happens there. The voltage and current curves change, the phase shift becomes greater, and the ellipse tends to flatten out. So what we've done here is we have constructed an equivalent out of the analog discovery of the SIG 101. So for those of you that wanted to buy a SIG 101 and couldn't find one, if you have an analog discovery 2, you can build one yourself. I'll show you the schematic again in a second for if you want a little bit of a refresh. But the basic idea is that you can do this with any function generator and any oscilloscope, two-channel oscilloscope, as long as you can do an XY display. But remember the caveat, you have to have a floating ground. So let's go back to the schematic and we'll talk a little more about that again. Okay, back to the schematic. You notice that what we had was a resistor across the black and red leads here. It turns out that resistor was exactly the same size as this resistor. You can vary this resistor based on how much voltage and current you want to measure. In other words, what the circuit is that you're working with. The reason that I chose a 1K across here and a 1K here to start is that made the display symmetric. In other words, the X and Y dimensions were the same. But obviously, if you have a much higher resistance here than you have here, well, then you get a different slope. Similarly, if you have a much lower resistance here than here. You can choose the resistor, and if you were building this, you might want to actually provide an ability to change this resistor value depending on the circuit you're working on. I pointed out that you need to make sure that this point will float. Well, notice what that point is. It's the negative input of channel 2 and the negative input of channel 1. Now, on most oscilloscopes, the negative input is connected to power ground. In other words, to the third wire, to the green wire. And so you can't use those kinds of oscilloscopes unless you float the ground. Now, I won't get into that because if you don't know what I'm talking about, you shouldn't try to do it. This point in the analog discovery is grounded, and most generators are grounded. In other words, this point is connected to the power ground as well, the third wire, the green wire, whatever. Obviously, if this point is connected to a ground and this point is connected to the same ground, this resistor is shorted out and this circuit won't work. So you have to be able to float this point. You can do that with the analog discovery because it has floating inputs. But be careful. If you use this device, which is the BNC adapter, that does not float the signals. The reason is this adapter for BNC connectors internally shorts this point, that is the negative of the scopes, the ground of the scopes, or to put it more succinctly, the barrel of these BNC connectors are all connected together. You can change the voltage on the center connector, but you can't, for example, change the voltage between these two barrels or between this barrel and this barrel. And those barrels are this point, and that point, and the ground of the other waveform generator as well. They're all connected together on the BNC board. So don't try to use the BNC board to do this experiment. It won't work. Okay, I hope that this has been helpful to people, maybe those who wanted to try a signature analyzer and were frustrated that Salig ran out of them or whatever. Up here on the this Digilant board is the connection. This is the 1K resistor, by the way, and I'm using the breakout board that you may have seen in an earlier video that you can buy from Digilant. You don't need the breakout board. You don't need any of this. You can wire this all up yourself. Just be sure you use the fly wires. That is, the connections that you see here. Get these capacitors out of the way from the previous part. The fly wires, not the BNC adapter board, to make these connections. It should work for you. By the way, for those of you that are interested in such things, the resistor substitution box that I'm using is one that I showed in a previous video about useful tools and gadgets. And the capacitor, or capacitors, that I was substituting are from this Sencor parts pack. The 0.5 microfarad and the 0.1 microfarad, and it has a bunch of others, but 2 is enough to show the difference. So at any rate, this is an attempt to help those who might want to do some experiments with one of these signature analyzers, but couldn't buy one of the SIG 101s, or perhaps didn't want to. But if you have an analog discovery, then here's a way to do it for the price of a resistor. I don't recommend that you go out and buy an analog discovery just to do this experiment. But where I am going to go is, in some future videos, is I am going to be trying to use a signature analyzer to see if it can help me in some of my vintage restorations. I'll take a look at a vintage radio, a 1930s radio, and see if using a signature analyzer to check out the radio before I ever try to power it up might help me identify the parts that I need to change, so that my first power up I may even get a working radio. Now, this goes in line with the idea that I've been putting forward recently, that maybe you don't want to just shotgun all of the vintage electrolytics. Now, let me be sure that everyone understands what I'm talking about, and I'll illustrate that in just a second. What I'm talking about when I say a vintage electrolytic is something like this, not a modern electrolytic like this. There were a lot of, particularly the younger hams, that were confused by that because they assumed all electrolytics were the same. And in terms of circuits, they are, but in terms of construction, they're quite different. Also, I'm not talking about the old paper capacitors like this. I think you ought to replace all of those. These were much more likely to fail short than the electrolytics. And many a transformer has bit the dust because one of these failed in an old radio and somebody didn't turn the power off soon enough. So I do advocate that you replace all of the old paper capacitors, wax and paper capacitors like this, in the old radios, but not necessarily the old electrolytics. Instead, what I suggest is maybe you might want to consider leaving them in if they still test good, and put a fuse in the power line. So look forward to some more videos, maybe using a signature analyzer on an old radio, or maybe on some other piece of equipment, or who knows. I never know where I'm going to go next, but it definitely will be somewhere. So I hope that you look forward to those, and thank you for watching. Have a nice day, and we will see you in a future video.